Now that sustainability is pretty much mainstream, sustainable design is pretty much mainstream in Europe, I find there are often two sentiments expressed. One is a kind of question about, okay, well, what's next? And the other is a slight sense of dissatisfaction with the word sustainable, which I think is very well captured by Amory Lovins when he says that, you know, if you were to ask one of your best friends, how's your relationship with your partner? And they were to respond, well, yeah, it's sustainable. You'd probably say, well, I'm really sorry to hear that. But there's something about that word that implies something that's just about good enough, just about bearable. And what I'm going to be talking about today is biomimicry, which I think is going to be one of the best sources of new ideas that will allow us to go beyond standard approaches to sustainable design and achieve restorative solutions. So let me just explain quickly what I mean by biomimicry. I'm sure quite a few of you are familiar with it. This image here, this is a highly magnified view of the scales on the butterfly wing. It's a blue morpho butterfly. And this shows how biology makes color effects. So humans, when we're making color, we often use quite toxic pigments, but some of the most vibrant color effects in nature are just tricks of the light. It's actually a microstructure that refracts the light and creates a color effect. And here's another example of a kind of miracle in biology. This is a bark beetle, which can detect a forest fire at about 80 kilometers. And it flies towards the fire, to where the fire's just passed through, and it lays its eggs in freshly burnt wood. Now, if you look at human-made fire detectors, I can't see one at the moment, but generally they have a range of about 10 meters. So this has a range of a sensitivity nearly 10,000 times that of human-made fire detectors. You might be sitting there wondering, why the hell would a beetle fly towards a fire? And it flies to where the fire has just passed through, and there's a kind of popular science explanation for why it does this, because when it gets to where the fire's just passed through, all its mates are there, it can have unlimited sex with no predators around, and you don't get much better than that in the beetle world. But the more serious point is it's an example of an adaptation to a really specific niche. And if we could learn how it detects the fires at that range, then we could create much better fire detectors ourselves. And what's more, this little creature here, it doesn't need a continuous connection back to a power station burning fossil fuels. And a further example, this is a rainforest plant called Anthurium warocquinum, which lives at the forest floor in very low light levels, and its leaves are covered in tiny, tiny lenses, which are able somehow to focus diffuse light onto the chloroplasts that allows it to thrive in very low light conditions. So if we could learn how to focus diffuse light, that would be a really interesting development. And I think the overall message there with biomimicry is that if we could learn to do things and make things the way that nature does, then we could achieve really radical increases in resource efficiency. And you could look at nature as being like a source book of solutions that have all benefited from 3.8 billion years of research and development. And given that level of investment, it kind of makes sense to make use of it. And just one more thing I want to say before I kind of get into the meat of the talk. A couple of people today have talked about saving the planet. And I think in some ways that's perhaps the wrong way of putting it, because you know, if humans were to disappear, the planet would get over us pretty quickly, actually. So what we're really talking about is people. And we're talking about whether we can create a really positive future. And I firmly believe that biomimicry is going to be one of the most important sources of solutions that will allow us to move from the industrial age to the ecological age of humankind. And in the way that I use biomimicry, I often talk about three big challenges that I think we need to bring about. And those are, firstly, achieving radical increases in resource efficiency, so achieving far more with far less. Shifting from linear, wasteful, and polluting ways of using resources to completely closed-loop models. And finally, shifting from a fossil fuel economy to a solar economy. And if we choose to embark on those three interlinked journeys, then I think there's no better source of solutions than biomimicry. And in the introduction, it was mentioned that I was involved in the Eden project, and this was I think it is the largest greenhouse in the world. And we used biomimicry all the way through that design process to completely rethink horticultural design. We looked at pollen grains and carbon molecules and marine microorganisms, and it was really the lessons from those super efficient biological structures that helped us achieve the breakthroughs that we did. And this superstructure was an incredibly lightweight solution. At the end of the project, I realized that I had a very accurate figure for the volume of air inside this building, and also an accurate figure for the weight of that superstructure. And it turned out that the weight of that superstructure was less than the weight of the air inside the building. And what we had found is that we got into a kind of positive cycle in which one breakthrough facilitated another. So with such large, lightweight pillows, as we called them, the cladding elements, which was an alternative to glass, we had bigger hexagons, which meant that we were getting more daylight in. We also saved on steel, so there was less steel weight. And with more daylight coming in, it meant we didn't have to put as much additional heat in during the colder times of the year. And with less overall weight in the superstructure, there were big savings in the foundations. So that, I think, is a fairly good example of how biomimicry can be used to rethink structures and produce a very efficient solution. And the main project I'm going to talk about is an office building where we've been using biomimicry to rethink conventional office design. And this involved a different design approach, actually. We said to the client that if we want to make a breakthrough, we need to approach this in a different way. Often, when architects work on buildings, often the big mistakes have already been made before the design team are even involved. The client may have chosen the wrong site, set the wrong brief, appointed the wrong team, and so on. So we persuaded the client that what we needed to do was to start with a concept study with an absolutely minimal brief. We needed to have an excellent design team, and we had to have a biologist as part of the design team. And selecting the design team was a little bit like the start of that cheesy cowboy film, The Magnificent Seven, where we got a chance to sort of choose the champion knife thrower and the best structural engineer and so on. We got together a really good team. And I think the other important thing about this was that it involved a certain suppression of the architect's ego. Often, architects, particularly of the contemporary iconic generation, they'll tend to do the sort of flashy sketch, and then they'll expect the rest of the design team to just make it real. And personally, I think that's quite insulting. If you've got a fantastic team, you need a process that allows you to draw out all the best ideas from the team, and the role of the architect is really to integrate those into a consistent whole. So this was what came out of the first workshop that we had, that we wanted to achieve a minimum 10% increase in productivity, for the building to be, as far as possible, passively self-heating and cooling, as far as possible entirely lit with daylight, for the building to be a net producer of energy, and for the air coming out to be cleaner than the air going in. And the last three there, I would argue, are going beyond sustainable to achieve this goal of restorative solutions. And one of the conclusions from this first workshop was that daylight, was likely to be the most powerful driver of the architectural form. And so with our biologist at the design table, we looked at a lot of examples of how daylight is gathered and distributed in biology. And I mean, light is pretty much a precondition for all life on Earth, so it's not surprising that there are ingenious ways of gathering it. And this is actually a spookfish, which has these amazing mirror eyes, which focus low-level bioluminescence onto its retina. We also looked at the stone plant. Now, this is a plant that lives in deserts, and most of the plant is below the ground for reasons of thermal stability. And then it has in the top what you could call a roof light that lets daylight in down to, let's call it, the basement where the photosynthetic matter is. And a third one that we looked at is the Brittle Star. Now, this is a kind of starfish that lives about 500 meters below the ocean surface, where light levels are very low, and it's evolved a covering of lenses over its entire skin. And those are near optically perfect lenses which focus small amounts of light and movement onto photoreceptors underneath. And by doing that, it's able to detect predators long before they see it. Now, all of these, I think, encouraged us to think much more deliberately and creatively about how to bring light into this building. A fairly conventional way of designing for daylight is to just think about what the optimum floor depth is, the distance between the window walls. And in the UK, there are plenty of examples of offices with 30-meter deep floor plates. And you know that with that kind of size, they're bound to be high-energy buildings, using a lot of artificial light and so on. We settled on a figure of about 12 meters between the windows as a good dimension to aim for. Then, thinking about the kind of building forms that this might suggest, one approach would be that we just take these narrow floor plates and we stack them up into a tower form. That would be fine if it was a very dense urban location with high land values. We were probably going to be dealing with an out-of-center site. So we looked at two other models. One was a kind of donut ring, where you have the floor plates arranged around a central atrium. And the third one was a more linear scheme, where you have two linear blocks with the light-admitting atrium down the middle. And it was the third one that seemed to work better when we analyzed the light levels. And what we found is that, looking at it in plan, we were getting a slight shading pattern along the middle of, a sort of curved shading pattern along the middle of those floors because of the effect of the opposite building block. So the next move was to just bend those so that it followed the pattern of the light, and we would get a very even quality of light all the way through. Now, this produced two further challenges. One was that narrow floor plates are not particularly good for creative clusters of people. And the second was that we were probably going to have to deal with a rectangular site. And this wasn't really making very good use of a rectangular site. So the next move was to elaborate these plan forms into these kind of undulating shapes in which we still had no more than about 6 meters from any point of the plan to the window wall. And now we were getting much better potential for creative clusters of people. The next step was to look at the building in section. And what we found is we were getting quite a lot more light than we needed at the top than at the bottom. And we did spend quite a bit of time looking at Anthurium veroquinum, that rainforest plant, to see if there were ways of actually harvesting light at the top and channeling it into fiber optic tubes so that we could conduct it down to the lower levels. It proved too challenging for this stage in terms of the technical development that was necessary, but it's an idea that we've parked and we want to come back to. The conclusion in section was that we needed to taper the building form slightly so that we bring light down into the middle. And we also proposed a large-scale light reflector in the atrium that would bounce light deeper into the lower floors. And then thinking about what might be underneath that large-scale light reflector, we thought that could be an opportunity to create a really dramatic meeting room, perhaps with some of the spatial qualities of the sets designed by Ken Adam, who designed the sets for Dr. Strangelove and James Bond and so on. And you know, we like James Bond, so we thought that was quite fun. And one of the big advantages of designing for high levels of daylight is that it's possible to grow a whole range of plants within the office space. And NASA did quite a bit of research on this, looking at what kind of plants could filter all the contaminants from indoor air. And they concluded that these 3 plants, in sufficient quantities, could take out nearly all the indoor contaminants. Money plant, I believe, is very good at oxygenating during the day. Mother-in-law's tongue produces oxygen at night. I don't know how. Areca palm is very good at taking volatile organic compounds out of the air. And all 3 of them are good at deionizing the air, which reduces dust levels. And there's been quite a big study, a 5,000 square meter office building in India that has tried this and has achieved really remarkable results. 20% increase in productivity, a 50% reduction in headaches and eye complaints, and even a measurable increase in blood oxygen level. And I think it's partly down to this concept of biophilia, which was a term coined by the biologist E.O. Wilson. And he hypothesized that humans are actually much happier and healthier when we're in direct contact with nature. Because we evolved in direct contact with nature for tens and hundreds of thousands of years, there's a lot of evidence now to suggest that we are actually physically better when we're in contact with nature. So alongside this, we were also doing work with genetic algorithms putting a model into a computer and setting parameters of daylight, surface area to floor area ratios, and a number of others, and letting it run through hundreds of thousands of iterations. And in a way, this is quite like evolution. You're creating hundreds of thousands of variations and mutations, and then you're letting the system weed out the most successful ones. And that was very useful for us in validating some of the predictions that we'd made during the first concept stage. Moving on to the structure, the way that we use biomimicry here was more about refining the structure. So it was the daylight that had driven the strategic form. So here we were looking to biomimicry to help us design much more efficient structures. And our resident biologist, a guy called Julian Vincent, says that you can characterize nature by saying that in biology, materials are expensive and design is cheap. So what you often find is really quite complex shapes that use an absolute minimum of materials. These are bird skulls, which are made of very, very thin layers of bones connected by struts and ties. So it's like a combination of dome technology and space frame technology, all in a humble garden bird. A similar one is Cuttlebone. Cuttlebone is, again, quite a complex structure. It's got these thin layers of bone, this time connected by undulating walls, which produce a very stiff and very lightweight structure. So then we analyzed a fairly typical column and slab arrangement of floors. And we analyzed it in terms of which bits of structure were working hard and which ones weren't. And all the bits that I'm about to shade in dark here, these are the bits that are structurally redundant. They're really not doing anything. So if the shape of the structure was to actually follow the shape that it wants to be, it would probably be something like this, where you'd have columns that taper towards the top. You'd have hollow columns. The floors would be slightly deeper in the middle, and then we would take out some of the mass of structure with voids. And then there's the potential to actually connect all those up into the air thermal control system, so that we're using the structure not just to hold the building up, but also to moderate the air. And it would only take a fairly modest departure from recognized technologies to achieve this. The big breakthrough technology for us would be 3D printing. At the moment, it's still really at a sort of prototype scale, but the great thing about this is that it allows you to be very specific about where you put the material. And as 3D printing increases in scale, we could start to produce elements of structure that are much closer to those examples we saw of the bird skull and Cuttlebone. The next part of this story was the thermoregulation. And in that last sketch animation, we saw how some pieces of structure can become more efficient when they become hollow. And in biology, hollow structures are normally used for something else. They're often used for conducting liquids or gases around the organism, or even in the case of our spinal column, it's conducting information. It's our nerve cells that connect our brain down to the rest of our body. And this suggested the idea of connecting the building into the ground underneath, where you have a very steady temperature. And you can find lots of examples of this in biology. Ground-burrowing animals do this exactly because it allows them to moderate the temperature in their burrows. And the accomplished masters of this are, of course, termites. Arguably, there is no higher maintenance monarch than the queen termite, who insists on temperatures in the egg-laying chamber of plus or minus ½ degrees C, even though the temperature outside is varying by as much as 40 degrees C. So our idea was to create a network of tubes in the ground underneath the building so that we could benefit from the steady temperature and use that for passive heating in winter and passive cooling in summer. And then we could use the hollow structure to bring it up into the building. A further thing that we could look at, perhaps in the next stage, is this idea of, it's called Murray's Law, which is a mathematical constant that governs the relative diameters of vessels in branching systems. There's a very consistent rule of proportion there, and also a consistent angle. And it seems to be an evolved minimum energy solution. Now moving on to the external envelope. Here we had quite a few things that we needed to achieve. We wanted to achieve high levels of daylight, mainly for human health, but also to reduce energy consumption. But of course, daylight varies enormously from 0 at night to as much as 100,000 lux on a really bright day. And in the working environment, you need a good deal more even than that. And in principle, what we needed to do was to admit exactly the right amount of light, which meant that we had to control the light coming in. And we decided that as a rule, as a design rule, daylight should be considered the most valuable form of energy, and the second most valuable form of energy is electricity. So the aim was to have some kind of control system on the outside of the building that would let in exactly the right amount of daylight, and it would convert all surplus light into electricity. In order to not lose too much heat, we needed a transparent insulation, and aerogels have come down in price a lot from being absolutely extortionate to just now plain unaffordable. But we have found something similar to this, actually based on polar bear fur. And the principle of converting light into electricity, obviously that leads us towards photovoltaics. And if we're to control the light, then it means these photovoltaics need to move. Now, both of those things sound expensive. But what we developed with our team, or what we learned from our facade experts, was that photovoltaics are much cheaper if you have a lot of small identical units rather than a fewer number of large customized units. And for things that move, they're a lot cheaper if they just move between two positions. If you're trying to get something to move through a whole range of positions, that's really expensive. But just an open and closed is a good deal cheaper. And then we looked at examples in biology of how this movement mechanism could work. So we looked at examples like the sensitive plant, Mimosa pudica, the iris, folding wing patterns in beetles, folding leaf patterns, unfolding petal patterns, and even Strelitzia, which actually changes its shape and geometry when the pollinator lands on it. And we haven't actually concluded this. This proved to be quite a challenging design problem, but we're going to come back to that in the next stage of the project. And we're very keen to develop some of these ideas from nature to produce an efficient and simple and cheap movement mechanism for the photovoltaics. We also looked at the skin of the building, and in biology there are lots of examples of efficient structures, like the sketches in the top right, that use curves for stiffness, so shells and leaves. And we're using a new technology of bending glass, which is a cold-formed glass bending technology that's much cheaper. And by putting together two pieces back to back like that, you can produce a very stiff glazing element which can span from floor to floor without a frame, and it uses about half as much glass as a conventional solution. And the other thing about that solution was that it would produce really quite a sort of soft texture to the outside of the building. And that was something that we really enjoyed about the Eden project. If those had all been flat glazing elements, I think it would have looked a lot more crude. And this is how the building looks at the end of the commercial feasibility study that we did. And the environmental engineer, that M&E consultant that worked on this, reckons that if it was built, it would be one of the lowest energy buildings in the world. And our workplace consultant said that in terms of the daylight and the floor plate efficiency, it was achieving unparalleled levels of efficiency. So commercially, a very attractive proposition as well. And we did a few sort of back-of-the-envelope calculations at the end of this, working out that the building was going to cost, let's say, about 90 million Swiss francs. And if there were 3,000 people in there and they were paid 100,000 Swiss francs a year, then the salary bill for the building is 300 million Swiss francs, which means that a 10% increase in productivity is worth 30 million Swiss francs a year, so the building would pay for itself in 3 years. It's surprisingly difficult to persuade clients of the validity of this, but I firmly believe that 10% increases in productivity are absolutely possible. That example in India, that achieved a 20% increase. And that's an indication of just how much difference daylight and biophilia can make to people's health and well-being. Okay, now moving on to the Mobius project. This is a project that explores ideas of moving from a linear wasteful, polluting way of using resources to a closed-loop model. And we've been talking about daylight in existing buildings, and certainly the radical refurbishment of existing buildings is an important part of the transformation we need, but we also need sustainable infrastructure in our buildings. So what I'm going to show is partly about that. And ecosystems, mature ecosystems, they work very differently to human-made systems. In mature ecosystems, all the resources are stewarded within closed-loop cycles, the water, the carbon, the nitrogen, and so on. And there have been some projects that have tried to mimic this. One close to here, Kalundborg, tried to co-locate a lot of industries. But my favorite one is a scheme called the Cardboard to Caviar project. And what happened here is that they collected cardboard from shops and restaurants. They then shredded it and they sold it to equestrian centers, horse centers, as horse bedding. When the cardboard was soiled, they collected the cardboard and manure. They put it into wormery composting systems, which produce worms, which they fed to Siberian sturgeon, which produced caviar, which they sold back to the restaurants. Which is quite nice because it's turned this linear wasteful system into a closed-loop system. And I'd been using this example for probably about 4 years in talks. And then I decided it was time I actually found out a bit more detail about it. So I invited myself up there, and the guy that set it up, a fantastic guy, Graham Wiles, showed me just how much he'd done. And in many ways, the bigger picture is more interesting, because it started out as just the first 2 stages. They were just collecting cardboard, and they were involving people with disabilities, shredding it and selling it to the equestrian centers. The equestrian centers said, okay, what do we do with all this manure and cardboard? So Graham said, all right, leave it with me, I'll have a think. And his first idea was to set up his own wormery composting system and sell worms to a fishing bait supplier. But at the 11th hour, the fishing bait supplier backed out of the deal. I don't know, the global market in worms had collapsed or something. So he said, all right, well, sod you, I'm going to cut out the middleman and set up my own fish farm. And this time he started working with reforming heroin addicts. Quite difficult kids that were costing the local authority as much as £100,000 per year on rehab programs with a 95% failure rate. Graham has achieved a 65% success rate with a fraction of that money. The next thing was that they found that the fish weren't putting on enough weight in winter because the water was too cold. By this stage, they'd been given a new, quite a big area of formerly industrial land by the local water treatment facility. So they used treated sewage sludge to rehabilitate the land, plant willow biomass to run a biomass boiler to heat the water in winter. The next thing was that Graham was having to spend a certain amount of money buying in fish food. And he didn't like this. He didn't like anything leaking out of his system, anything wasted, any money leaking out of it. So he got the kids growing vegetables to make fish food. As it turned out, the reforming heroin addicts ate all the vegetables, but that was actually a good thing, because prior to that, they were just coming to the site every day with a can of Coke and a Mars bar for their lunch. So it's no wonder that kids have behavioral challenges. And then the next thing was that they planted up new areas of this former industrial land, growing orchards to sell more stuff back to the restaurant. And then they used plants to treat the wastewater from the fish tanks, producing watercress, so another product to sell to the restaurant. Then he heard that there was a bakery chucking out loads of moldy bread every day. And apparently you can grow maggots on bread with none of the smells associated with meat-based production. So that was another foodstuff for the fish. And a new one that's more recent is that he set up a smokehouse to add value to the fish. And this time he's working with people who've come back from conflict zones, people with disabilities and post-traumatic stress disorder. And a shocking number of those people in the UK actually end up in prison. And whatever we might think of the rights and wrongs of the Iraq War, these are people who have made a big sacrifice to society and deserve to be better treated. Now, what I think is amazing about this is that it has evolved like an ecosystem. And at every point at which he found he had a problem, he thought about what he could add to that system to create more value, to transform waste into value. And he's been inventive with waste at every level. He's reintegrated, He's involved physical waste from the local environment, but also he's been inventive with what is arguably the most deplorable form of waste, and that is underutilized human resources. He's managed to reintegrate people with disabilities, reforming heroin addicts, and people from conflict zones in a regenerative system that really adds value and boosts biodiversity. And this actually shares a lot of the characteristics of ecosystems. If we compare the typical characteristics of human-made systems with those of biological systems, ours tend to be simple and disconnected. Biology is complex and interconnected. Ours are linear and wasteful. Biology is closed loop and zero waste. I don't necessarily need to go through all of these, but I think if you look down that right-hand list, that's actually a really good summary of what we need to do to transform our cities and our industries and our buildings. And those are the kind of challenges that we need to bring about to create the ecological age. So we've been working with these on an idea for an urban greenhouse, similar to this one in Amsterdam. This is called De Cas, where a restaurant was set up within a productive greenhouse. We also wanted to have an anaerobic biodigester, so we could bring in all the biodegradable waste from the local urban area, turn that into fertilizer and energy. We wanted to treat the wastewater using plants and microorganisms. This is a technology called living machines. We had to have a fish farm, obviously, that would be supplied with vegetable waste from the kitchen and would supply fish back to the restaurant. This was proposed for central London, so we thought it would be quite fun to have a coffee shop. And the spent grains from coffee are actually an ideal substrate for growing mushrooms. So what we're doing is we're bringing together cycles of food, energy, water, and waste in a way that tries to hook these all up so that they're more productive. And just for fun, we chose a really challenging site. This is in central London. It's a complete eyesore. It's this roundabout that no one can get to. But with a fairly small amount of replanning, that could be transformed into a space for people that reconnects people with food, energy, water, and waste, and transforms these big challenges of cities into major closed-loop opportunities. So if we think about the whole metabolism of our cities and think of those waste streams as opportunities to create value, then we could really start to make progress. The final project I'm going to talk about in the last 7 minutes is the Sahara Forest Project. And this is one we've been working on for 5 years. And it came as quite a surprise to us when we were reading about deserts to learn that a lot of the world's deserts were actually vegetated a fairly short time ago. When Julius Caesar arrived in North Africa, what he found was this wooded landscape of cedar trees and cypress trees. And his armies set about clearing all that to set up intensive farms that supplied grain back to the Roman Empire. And for 200 years, that is what it did. But after that period of time, they found that they had substantially trashed the landscape. The fertility of the soil had been depleted, the rainfall patterns had been massively reduced, and nearly all the minerals from those soils in the deserts had been processed through the collective digestive system of the Roman Empire out into the sea. So a classic linear, extractive, wasteful system. So in many ways, deserts are the result of our activity. But I think a big part of resolving our energy challenges lies in actually looking at the deserts as opportunities. In many ways, they're zones of massively oversupplied with daylight. So we need to capture more of that. And the idea of shifting from a fossil fuel economy to a solar economy is not as challenging as perhaps. If you look at the amount of energy that we receive from the sun, we receive about 7,000 times as much energy every year from the sun as we use in energy from all forms. So I'm not suggesting it's going to be easy to make this shift, but that statistic of 7,000 to 1 does at least suggest that the solar economy is possible. It's a challenge to our ingenuity. The other thing about deserts is that most biologists agree that it was the colonization of the land by plants that helped produce the benign climate we currently enjoy. And if you look at this, I'll just run that once more. This shows photosynthetic activity around the world over the course of a number of years. And if you look at the edges of those deserts, you can see that the edges move back and forth over the course of each year, which raises the question of whether we could intervene at those points to halt or even reverse desertification. And I think there's a really urgent case for this because A lot of these very arid countries are going to be suffering from climate change. They're going to be getting less rainfall, but they're having growing populations. And this study makes the point quite well. This was a study into the connections between food price and civil unrest. And what the academics did is they mapped all the examples of civil unrest around the world, and then they mapped that against the food price index. What I don't think they did, at least I couldn't read it in the report, is they didn't map onto that an oil price. But actually, there's a very close match between oil price and food price. So with oil prices, the long-term trend steadily going upwards, unless we deal with this, it means that civil unrest and food riots are likely to become more and more common. So it's really important that we find a way to shift food production away from its fossil fuel dependency, and just to make more use of natural light and solar energy. Now, when you're working in a desert, there's a lot you can learn from the organisms that are already adapted to life there. This is a beetle that has learned to harvest its own fresh water in the desert. It comes out of its hiding place at night, it crawls to the top of a sand dune, and it's able to radiate heat out to the night sky and become slightly cooler than its surroundings. So when the moist breeze blows in off the sea, you get these droplets of water forming on the beetle's shell. Just before the sun comes up, it tips its shell up, water runs down to its mouth, has a good drink, goes off and hides the rest of the day. Not a great quality of life, but it's a clever trick, and that's good enough for me. Its ingenuity, if you could call it that, goes even further, because it's got these little bumps on its shell, which are hydrophilic. They attract water, and between them there's a waxy finish which repels water. And the effect of this is that as the droplets form, they stay in very tight spherical form, which means they're much more mobile than they would be if it was just a sort of mist over the whole shell. So even when there's only a small amount of moisture in the air, it's still able to harvest that water very efficiently and channel it down to its mouth. Now, I'm running a little bit short of time, so I'm going to have to skip this one. But what we're doing is that we're using a greenhouse that is based on the fog-basking beetle, and it uses salt water as the input, and we evaporate salt water into the greenhouse to make a cool, humid growing environment, and then we capture some of that humidity as fresh water in a process similar to the beetle. And then, following the biomimetic principle that you need to always look for symbiotic relationships if you can, we looked for other technologies that could work well with the greenhouse, and we settled on concentrated solar power. This focused the sun's heat to create electricity. And the two technologies have very interesting synergies. Firstly, they both work very well in hot, sunny deserts. We can make the concentrated solar power more efficient with the seawater cooling. And the shade created by the mirrors makes it possible to grow a whole range of plants underneath that would not grow in direct sunlight. So what we're proposing is a kind of long hedge of greenhouses fed with seawater and with concentrated solar power plants at intervals along the way. So it's a model for how we could create zero-carbon food in some of the most water-stressed parts of the planet, as well as generating renewable energy and revegetating deserts and locking up atmospheric carbon in desert soils. We're also looking at how we can transform the waste salts into useful, commercially extractable compounds. And we're looking at a whole range of other technologies that could be synergistic in this system. Algae, halophytes, which are salt-loving plants. And these are evaporator hedges, which enhance the restorative benefits of the project, enable us to grow stuff in desert soils. And then we've been analyzing these in terms of their resource inputs and outputs. And the intention is to get these all to hook up into a densely interconnected system that mimics the kind of amazing, complex, but highly efficient and productive systems that you find in biology. We've just finished building a pilot version of this in Qatar. And soon we hope to be moving on to building a version of this in Jordan, which has absolutely ideal conditions. And over the course of the next few years, we'll be looking at a whole range of examples from biology to help us optimize this system, such as camel's nostrils, which are a miracle of water recovery, heat exchange design. The sand skink, which can swim in sand without suffering any scratches. Maybe we could make scratch-proof coatings for our mirrors. Maybe we could even make mirrors at room temperature like the beetle does, just out of proteins. The thorny devil, that drinks with its feet. The water tracks up, it grooves in its skin to its mouth. And Just to draw together some conclusions now, coming back to those three challenges that I mentioned of radical increases in resource efficiency, shifting to closed-loop models, and shifting to the solar economy. I firmly believe that biomimicry is going to be a really powerful source of solutions. And it's also a way for us to talk much more positively, I think. Too often, environmentalists use very negative language. It's all about cutting, reducing, eliminating. But actually creating the ecological age involves creating a better quality of life, healthier buildings with more daylight, fresher food and cleaner air. And people sometimes ask me if I'm an optimist or a pessimist. And I think that's in many ways the wrong question, because both of those positions imply some kind of inevitability about the future. And the future is not inevitable. I believe we need to decide on the future we want to create and then set about creating it. And that idea of creating the future is not as strange as it might sound. Yeah, sure, you can let the future happen to you, or you can decide to shape the future. And if you consciously do, shaping the future is what you do every moment of your waking life. Moment to moment to moment, you are shaping the future. And that destination of the ecological age, I really think that is close enough to touch now. And I firmly believe that biomimicry will help all those that want to make that journey. Thank you very much.